Okay, Calc, we are still in section 4.2. This is the second half. We're going to start with number 4 down here at the bottom, and then we'll do the whole backside for notes. But just as a review, this section is all about the power rule. And so just as a review for power rule, this is written down at the top. But if you are trying to find the derivative of like x to the nth power, you would pull the n down in front, leave the x, and then subtract 1 from the exponent. So like the derivative of like x to the 5th power would end up being 5x to the 4th. If you have a number already in front of x, so like 2x to the 3rd, let's say, when you pull that 3 down in front, all you do is multiply it. So that would be 6x to the 2nd power is what that would look like, okay? So that's just kind of a review of what the power rule looks like. And then it gets a little bit more complicated when you have, like square roots and, like the x's in the denominator and stuff. So in number 4, this is what we're looking at. We're looking at the 3x on the bottom being to the -2 power, okay? So one way of thinking about that is that the 3 is to the -2 power and the x is to the -2 power. And typically we don't like negative exponents. So what I'm going to do is I'm going to bring both of those actually to the top. And so this 7, the 3 will now, it's going to be multiplied by 3 to the 2nd power and x to the 2nd power. So those if you need to think about it as having 1 on the bottom, moving both of those to the top will move those or make those positive exponents. 3 to the 2nd power is 9. And so this actually is just 63x squared before we take the derivative. So that's like the rewrite step, right? 63x squared. And then actually, when we take the derivative, we just multiply the 2 down in front. That's going to be like 126x to the 1st power, or just 126x to the 1st. And really, after we take the derivative, the differentiate step, right, is y equals 126x. We actually don't have to simplify anything because it's already simplified. By moving that to the top, we made those exponents positive, and it actually kind of, made the answer a lot nicer for us than any of the previous 3 problems that we did yesterday. So that's kind of how that works out. There you go. Let's go to the backside. The backside, sum and difference rules. Sum means when you're adding terms together. Difference means when you're subtracting terms. So like when you have there's 3 terms here. The sum and difference rules, all this means is that when you have multiple terms, like this is a trinomial, you're just going to take the derivative individually of each one. Like you just look at them as the individual terms and take the derivative. So like the derivative of x to the 3rd power is 3x squared. The derivative of -4x, this is like to the 1st power, okay? So keep in mind the 1 comes down in front, and 1 times -4 stays -4. But this will be x to the 0 power, right? 1 minus 1 would be 0. And then the derivative of any constant number, this is like x to the 0 power again. We take 0 down in front, 0 times 5, and this would be x to the -1st power. But 0 times anything is 0, right? We said the derivative of any constant is just 0, okay? So we call this f prime of x. That's his derivative's name, and he will be 3x squared minus 4, okay? So just as kind of a little hint, let's go back up to the original guy. Okay, the original, we said that when you take the derivative of any constant, it can become 0, okay? There's also another little thing, another little tidbit that says if you were to take the derivative of any linear term, meaning x to the 1st power, it's just going to come out to be the constant in front of that, right? Because like the x is basically just going to drop off the end, right? So if you can remember that, that can be kind of a little shortcut for you as well, and you don't have to think about it so hard. It's just that like if it's a linear term, like x to the 1st power, it's just going to be, the derivative is just going to be that number in the front, so -4 in this case, okay? So here is the derivative. Now, again, this is just what's called the general derivative. They would have to say, okay, now we want the slope, the derivative, at a specific point. So at the point, 1 comma something, and then we would plug 1 in for x or whatever, right, to get an actual number for the slope or the derivative, right? This is the general derivative. But anyway, that's coming, okay? All right, the next one, number 2. This one is a little bit ugly looking just in the first term, And I'm going to make that look a little bit better. This x to the fourth power really is in the numerator. And what I'm going to do is I'm going to make that look like negative 1/2 x to the fourth power. I'm going to slide this x to the fourth off to the side, and then it makes it really easy from there. So from here, I just take the derivative of this, which means I take the 4 and multiply it down in front, okay? 4 times negative 1/2 is negative 2. X to the, I subtract 1, so that's 3 now, okay? So that was very easy to find the derivative after we just rewrote it to be something nicer. This guy's derivative, I multiply the 3 down in front. 3 times 3 is 9, and this is x to the second power, okay? Here's that linear term again, so this is the first power, right? 1 times negative 2 is negative 2. This would be x to the 0 power if we subtract 1, or just like nothing. It's just that constant in front, okay? You gotta take him out of here. So, linear term, you have to just like take the constant off of the front of it because the x just drops off in the derivative, okay? Our name would be g prime of x, and that is my general derivative, okay? Again, if we were finding it at a specific point, I would plug that in for x to find the actual value of the slope at that point, but, you know, this will do for now, okay? All right, rates of change. We always talk about the derivative being a slope, right? Derivative equals slope of tangent line. If you don't remember anything, remember that. And a slope is a rate of change, okay? At one point in time, I think we wrote down something about like how the first derivative represents the velocity. A lot of times of like a moving object. The second derivative will represent the acceleration. I don't think they have us do acceleration today. But first derivative is velocity, second derivative is acceleration. So just remember that when we're finding average velocity, we're calculating the second derivative. If we're just dealing with the function, like this function right here, it says a billiard ball is dropped from a height. This function is just going to tell me what the height is. So at a certain time, this is what the height is. This is the function for height. If I take the derivative of that, that will actually give me the velocity at that specific time. So that's what we're going to do here in a second. Okay. All right. So a billiard ball is dropped from a height of 100 feet. That's where the 100 comes into play. Oh, do you guys remember the negative 16? That's the acceleration due to gravity in feet per second. It's like 9.8 meters per second, if you remember that from physics. But there you go. There's where your numbers come from, your function. 100 is my starting height. Negative 16 is my acceleration due to gravity. Okay. S is measured in feet, and T is measured in seconds. So at a time of whatever, I can figure out what my height is, okay? Find the average velocity over each time, over each time interval. That should be a space right there. Over each time interval. Okay, so this one is just saying average velocity. We don't need to know the specific velocity at a specific period of time. We're just looking at average velocity. So like right now, what we're doing is from 1 second to 2 seconds, how fast is it traveling? Okay, so 1 second, it's at a height of something, and 2 seconds, it's at a height of something. We just got to know something like this in trig, actually. These two numbers are actually both your x's, and you're trying to find what the y coordinate is. So at a time of 1 second, if I plug 1 in here, this would end up being, I think, 84 when you plug it all in, okay? If I plug in 2 seconds, 2 squared is 4 times 16 is negative 64, and I add 100, that's 36. And then what I would do is I would take and just find the average velocity, the average rate of change, okay, which means find the slope between those 2 points, okay? 36 minus 84 over 2 minus 1, which is 1 on the bottom, and I don't know, whatever that is, 48, I don't know, something like that, negative 48. So it's going negative 48 feet per second, okay? Now, we did not have to use a derivative on that because we were looking at the time interval from 1 second to 2 seconds, okay? A derivative is going to give me an instantaneous rate of change, like what is the velocity at 1 second exactly. I'm talking about the average rate of change over a time period. So that's how I get away with not having to do derivative and just having to do slope. I'm talking about average rate of change versus instantaneous rate of change, okay? So if you think about this as like a curve, like, You know, what's happening is my ball is being dropped, right? We're talking about from 1 second to 2 seconds. What is my rate of change here? So I have a secant line, and I do have 2 points where I can find a slope from. If I was asking for instantaneous rate of change, like I only want to know the slope at 1 second, that's when I would have to use a derivative, because that's a tangent line and not a secant line. I don't have 2 points anymore where I can do slope. I only have 1 point, okay? So rewind that if that didn't make any sense, and see if listening to it one more time would make sense. Part B is the same thing as part A, 1 comma something and 1.5 comma something. We're just going to find the slope there. So I know 1 is at 84 and 1.5. This is where I don't have, do I have a calculator maybe? Let's see what I've got. Yep, we'll try it. 1.5. I'm going to plug in for t, so I'm plugging 1.5 in here. So I'm taking 1.5 and squaring it. And it's 2.25 times 16, or negative 16, and then I subtract that from 100. So this is 64, I believe. So it's 64. Then I would do 64 minus 84 over 1.5 minus 1, which is negative 20. Negative 20 over 0.5, which is negative 40. So on average, it is traveling 40 feet per second rather than 48 feet per second, okay? And this should make sense. From 1 second to 2 seconds, it's falling a whole second. And so the longer it's been falling, the faster it will be traveling. Here, it's only been traveling from 1 to 1.5 seconds. So it's only been traveling a half of a second, in which case it's not going to be traveling as fast. This one is going to be the same trend, where it's only been traveling 0.1 seconds. So it's going to be not like even less than 40, because it has not been falling as long, okay? All right, so 1 we said was at 84. Now let me figure out what 1.1 is. Okay, I got 80.64. Okay, so 80.64 minus 84 over 1.1 minus 1. Okay, so I get 3.36 over just 0.1. Okay. And one thing you can do is, rather than actually dividing that out in your calculator, just move the decimal one place. So this is 33.6 over 1, or just 33.6 feet per second. So just like we had said, it hasn't been traveling as long as what it was in part B or part C. Here it's only been traveling 0.1 second. Here it's been traveling 0.5 seconds. Here it's been traveling a whole second. So it's going to be moving fastest at this point. And slowest at this point, because it hasn't been traveling as long, okay? Again, that's average velocity, or average rate of change. We're going over a specific time period, looking at a secant line, so I can do a slope, rather than instantaneous rate of change, which is what we're going to do down here, and that's going to involve a derivative, okay? So here we did not need derivative, because we were doing over a specific time period, so 2 points, okay? Here we will be looking at 1 point specifically, okay? So here we go. A diver jumps from a platform, and it's doing kind of a parabolic thing. So it's going, like, it's jumping up and then it's coming back down. That's a very, like, skinny parabola. But anyway, you get the idea, okay? And the platform is 32 feet in the air. Hence, in the equation, this is where your 32 is, okay? But the fact that he is jumping upward is going to give me that middle term in my equation here. So he's jumping upward rather than just jumping straight down. So here we were just dropping it straight down, therefore I didn't have a middle term, but here I have a middle term. That negative 16 again is that acceleration due to gravity, so that's how kind of we set up our equation. Blah, 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 that stuff. Okay, all right, here we go. This S of t will just tell me where the height of the diver is. So after 1 second, I can plug in and I can find how high up in the air the diver is, right? He's starting at 32, he jumps up a little bit, and then he comes back down, okay? All right, when does the diver hit the water, okay? When. That means we're solving for t, right? When means find the time. And the diver hits the water at a height of 0. So this is not asking for derivative. It's not asking for velocity. That's in part B, okay? So they're asking for, I'm going to do part A down here so I have a little bit more room to work. They're asking for, at a height of 0, how long does it take to get there? So I have this stuff going on, okay? All right, so we're solving for t. This is a trinomial, but it's not a simple trinomial yet unless I divide everything by negative 16, because everything's divisible by negative 16, even 0. So 0 equals, this will just be t squared. This will be minus 1t, and this will be minus 2. Okay, now from here, this is a simple trinomial. So what can you multiply to get negative 2? But when you add them, give you negative 1. And this is t, I wanted to say x there, t minus 2 and t plus 1, right? That'll give me that. And then when I set them equal to 0, my time will either be 2 seconds or my time will be negative 1 second, okay? Those are my two answers. Now, negative 1 cannot be a solution, right? Like negative 1 seconds on here would be like right here. This is negative 1 second, right? This is at a time of 0. So he's going up, coming back down. This is at a time of 2 seconds, right? So at a time of 2 seconds is when he hits the ground, okay? Now, here's the deal. What is the diver's velocity at impact, okay? Now, we needed to compute part A because we needed to know how long does it take for impact, right? At what time do we hit impact, okay? That's where the t equals 2 comes into play because we know, okay, it takes 2 seconds to hit impact. That's why we need to define part A first, okay? Now we're just calculating the velocity or how fast at the instant he hits impact, impacts the ground or impacts the water. How fast is he going at the instant of 2? It's not like over an interval, right? Like it was up here where we could just do slope. I want to know exactly at time 2 how fast he's going, okay? So that's going to involve me taking the derivative, okay? And I'm going to take the derivative of this equation right here. Velocity is a first derivative. So I take the first derivative. I'm going to take 2, multiply down in front. So that is negative 32 t to the first power, okay? Plus the derivative of 16t is just 16, right? Okay, that's a linear term, so the t just goes away. Or think about it as like the 1 up at the top, 1 multiplied by 16, you know, t to the 0 power, whatever. The derivative of 32 is plus 0, so he goes away. So this is my derivative. This is my s prime of t, okay? That's what my derivative is. I want to know at impact, which means at a time of 2, because that's what we found impact to be. At a time of 2, I'm going to plug 2 in here. Negative 32 times 2 plus 16. This is negative 64 plus 16, which equals negative, I don't know, negative 48 feet per second. Okay. Velocity is a lot of times negative because we're falling toward the earth. So we're falling downward. We have a downward motion. So that's why your velocity is negative. So don't let that like confuse you too much. But velocity a lot of times is negative when it's falling. So 48 feet per second is how fast we're traveling at exactly, 2 seconds at exact impact. We are hitting the water at 48 feet per second. And that's how that works, okay? So we do velocity by finding the derivative, okay? I hope that made sense to you. All right, homework assignment is this stuff. I don't know. These are just the basic power rule. I went ahead and did number 5, so you can look at number 5 if you want to, and see that is just doing those. Trying to think. Number 8, if you want to take a look at number 8, you can pause on number 8. There is that simplified. So these are a lot of these are just the same as what we did on our homework. And then we got story problems on the backside, and I'm not going to scroll down any further because I don't want you to see those yet. So attempt those, do as much as you can, and then we'll answer some questions tomorrow. Okay?